Hello, everyone. I'm Shaojie Chen from Beijing University. My presentation title is SSLTLS Encrypted Traffic Application Layer Protocol and Device Classification. The first part is the problem description. SSL encryption technology has the advantages of high security and low cost. It is widely used for secure communication. The protocol and device classification of encrypted network traffic are the basis of the network device quality and the network security technologies. Traditional traffic classification technologies, such as deep packet inspection, have difficult detecting encrypted traffic. To solve these problems, many machine learning and deep learning methods are used. Here are the existing methods. For protocol classification, port-based method and deep packet inspection are used. In recent years, port-based methods have not been more effective due to the widely use of dynamic ports and continuously emerged new applications. And deep packet inspection classifies traffic through pattern matching or the payload in the packet. It is still difficult to adapt to the encrypted network environment. For device classification, some traditional machine learning method and deep learning method appeared. For traditional machine learning methods, they extract features such as packet length, packet ordering, and packet timing, and then classify the features with machine learning models. However, feature engineering requires much time and professional knowledge to support. For deep learning method, CNN and RNN models are used for packet data or extracted sequence features. And this method could directly deal with packet data and could achieve good classification performance. To sum up, research or application layer protocol classification of SSL encrypted traffic is still lacking. For device classification, traditional machine learning methods do not make full use of the semantics of the packet content. Existing deep learning-based methods only use the first few packets of the SSL flow. The content is not portrayed from global level of the flow. To address the shortcomings of the existing method, we propose a new SSL application layer protocol classification method. It combines ciphertext features and a voting scheme. The method first extracts ciphertext features and use a machine learning model to classify the protocol of single packets. Then we use a voting schemes to realize the application layer protocol classification of SSL sessions. And then we propose an HTTP device classification method based on feature engineering and deep learning. This method establishes a CNN-LSTM model to extract the time series features of the packet and merge them with the global features of the session. To evaluate the performance of our method, we construct a dataset from many sources, include Chrome, Foxmail, FileZilla, and so on. The following part is the overall framework. Here is the framework of the two-layer classification model. Our method is divided into a training phase and a testing phase. In the training phase, we separately train protocol classification model and the HTTPS device classification model. And in the testing phase, we first do the protocol classification for the traffic, and then do the device classification. Our method regards SSL sessions as detecting unit. We mainly focus on 5 application layer protocols, including HTTPS, FTPS, SMTPS, IMAPS, and POPS, and 5 HTTPS devices types, including browser, streaming, chat, mail, and file transfer. In the training phase, the dataset is divided into two parts, which are an application layer protocol training dataset and an HTTP service training dataset. The protocol classification model and the HTTPS service classification model are separately trained on the corresponding dataset. In the testing phase, the protocol classification model is used to identify the application layer protocol, and then the sessions which are classified as HTTPS are further used to classify the service using the CGSF model. Finally, the services of all sessions are output. Before training the model, we need to pre-process the data. We first restore the raw flow to sessions based on a for tuple, which include source IP, source port, destination IP, and destination port. And we discard the incomplete SSL session due to being truncated or from network delay, and only retain the complete sessions for experiments. The following part is about our application layer protocol classification. Here is the framework of our application layer protocol classification method. We use SSL sessions as determination unit. We extract the features from each packet data and then make classification. And we vote on the prediction label of each packet and obtain the labels of the session. This method is based on feature engineering. Our method is mainly divided into feature extraction, single packet classification, and voting. We extract all application data protocol packets in every session, extract the packet's application data fields, and then do the feature extraction. The features from each packet are input into the classifier and obtain the protocol label. And finally, vote on the prediction result of single packets and select the application layer protocols with the highest frequency and the label of the session. We refer to randomness detection and the ciphertext entropy theories mentioned in other papers, and design the features including randomness measurement, entropy, length, and bidirectional flow. Randomness measurement is an important indicator for evaluating the randomness of the ciphertext. When the plaintext content of different package format is encrypted, the distribution of these characteristic values is still different. Entropy can be used to indicate the uniformity of the ciphertext byte distribution. The more uniform the byte distribution is, the higher the entropy is. We also use the length features because different protocols have different length distributions. For example, the length of FTPS data packets and the HTTPS packets are usually hundreds of bytes or even reach the MTU, but the length of other protocols packets are relatively short. The bidirectional flow features are mainly for FTPS data packets, which are all unidirectional in the SSL encrypted transmission stage, while other protocols are usually bidirectional. In the selection of classification models, we consider the current popular machine learning algorithms, which are mainly divided into three categories, which are traditional machine learning, ensemble learning, and neural networks. The next part is about our service classification model. Among the existing service classification methods, machine learning only uses the time and the length features of the network flow. Deep learning method only focus on the content of the first few packets of the session. Both of them lack the macro description of the entire network flow. Therefore, we propose a CGSF model that integrates the global feature of the session with the packet time sequence information. The features contains two parts, which are 23-dimensional global features and the packet time sequence information. The global feature is time-related features, such as duration of the flow bytes per second, and so on. For sequence information, we use the first n bytes of the first n packets of the session as the input. Here, the Ethernet frame of the packets are discarded, and we replace the source and destination IP with zeros to reduce the influence of this unnecessary information. Then we convert data packets into bytes to obtain the sequence, and then divide each byte value by 255 for normalization. The classification model uses both global features and sequences as input, which could integrate the two kinds of features. Here are the details of the model. The left branch of the model pre-processes the global features of the session, which input dimension is 23 plus 1. First, the input is flattened to 23 dimensions. Then, through two full connected layers, the output is 128-dimensional vector. The multiple branches on the right extract the time sequence features from packets. The input is the first n byte stream of the first n packets of the session. The first n packets are selected because the first few packets of the session are in the handshake phase and contain certain semantic information. When the encrypted communication is turned on, the semantics will be greatly weakened. We use CNN to extract the features of each packet by stream. The CNN layers include three concatenated 1D convolution, max pooling, and dropout. After that, the features of these sequential packets are concatenated and input into the LSTM to extract the time sequence features. Then 100-dimensional time sequence features and 128-dimensional global features vector are integrated and input to three full connected layers. Finally, the classification result is output through a softmax layer. The next is about our experiments. The first is our dataset. We connect network traffic by many application clients in the laboratory environment and use Wireshark to capture network traffic and store as PCAM files. In total, we capture 51 PCAM files and with total size of 4.7 GB, which include 5 application protocols, and in which HTTPS includes 5 service types. Then we construct 2 datasets with the traffic. For protocol dataset, the 5 protocols are regarded as 5 classes. In the upper application layer classification task, we further divide FTPS into FTPS control and FTPS data, and we obtained 6 classes. And for service dataset, 5 types of HTTPS services are regarded as 5 classes. Here are the details of our dataset, which contains multiple sources. For indicators, we applied accuracy rate, precision, recall, and F1 score, and we mainly focus on the accuracy rate. The first experiment is to compare the effects of different classification models. We try 4 traditional machine learning methods, 5 example learning algorithms, and 2 neural network methods. Here, we design 2 schemes for 5 classes and 6 classes according to weather divided FTPS into two classes. For packet detection, we selected 8,000 packets for each protocol and divided into train and the test set at a ratio of 4:1. And for session detection, we select 150 sessions from each protocol. Here are the effects of the models. From the result, we could find that XGBoost performs best on single packet classification and 6-class session classification, while GBDT performs slightly better than XGBoost on 5-class session classification. On the whole, XGBoost is the most comprehensive model. The table here shows the detailed experiment result of XGBoost, and the figure is the confusion matrix of single packet result of the XGBoost. We could find that for session detection, the F1 score could stabilize about 99%. The second experiment is to compare our SWICE classification model with the existing method. Here, we choose 6 methods from 5 papers to do the comparison, which are from 2016 to 2020. The table are the accuracy of our method and the 6 existing methods. From table, we could find that our method has the best accuracy, which reaches 96%. The third experiment, we explore the influence of N and M to our SWICE classification method. N here represents the numbers of packets we selected in each session, which is ranged from 3 to 10. And M means how many bytes we choose from each packet, which is ranged from 500 to 1,000 with a stamp of 100. We compare the accuracy of each pair of N and M. For the result, we could find that the model achieves the best performance with 2 pairs of N and M, which are N equals to 6, M equals to 800, and N equals to 6, M equals to 1,000. We find that when N is too small, the information in the handshake phase will be incomplete, and when N is too large, encrypted data will be used, which will have a certain negative impact on the model performance. When M is too small, the information extraction of each packet will be insufficient, and when M is too large, it will have a certain impact on the computational performance overhead of the model. There are 2 pairs of parameters achieves the best performance, but considering the calculation cost of the model, we finally choose N equals 6 and M equals to 800 as the final parameters. The fourth experiment is to compare the effects of the SWICE classification model, whether introducing the global features. From the result, we could find that when introducing the global features, the model could better characterize the sessions. The last part is our conclusion. We propose a 2-level application layer protocol classification model that combines packets and sessions information to classify the application layer protocol. We propose the CRN-CGSF model combining session global features and packet time sequence features for HTTPS SWICE classification. We have conducted many experiments on the dataset constructed in a laboratory environment. Our method is better than the existing machine learning and deep learning method. That's all. Thank you for your listening.